That's okay. I'll start the recording. Happy Garbage Day. Happy Tuesday. Welcome back. We have a new unit to talk about. Nothing was due last night, but I did update grades anyway, so you should be able to see where you stand with respect to the work that you've completed. Currently in progress is homework 4 over item factor analysis models for binary data and ordinal data. Also in progress, if you would like to or want to do a revision to your homework 3, that's also due by next Monday. If you're not sure what you need to fix, please send me an email and I'll happily clarify that. If you look at your score and you're like, yeah, 14.5 out of 15 is good enough for me, it's good enough for me too. So it is optional. But if you want to take the chance to make it, to fix all the errors so that you have a complete, finished version for your own reference later, that's always a good strategy. So that's one of the things I hope to leave with you is examples for your future self to use as you write up these analyses and proceed with this knowledge base. So any questions on homework 4 or other work that's in progress? We can start there. As I mentioned a couple of emails, I did figure out an error in the answer key. So thanks to those of you who sent me emails about that, I was able to track down what had happened and adjust the data set accordingly. And if you had answer 39 correct, I gave you the credit for it and fixed all of that. So that everything should be okay now, but let me know if you get stuck on something else. Sometimes it's my fault and not yours. So we did figure out what the problem was, that you and I were going back and forth with this. I had the answer from a different, it was either a different model or a different data set, because I do change the data out so that not everybody's answers are the same from semester to semester. So if not, then are we ready for something new? Why not? That was kind of a rhetorical question, to be fair, because whether we're ready or not, that's what the plan is for today. So unless there's questions about earlier stuff. So we'll get the screen share going. I have the recording going. Everything else should be ready to go. So this unit 7, is probably going to take this week for sure. We'll see if it goes into next week. It'll depend on how quickly we can go through this. It is covering a topic that is often of interest, both in educational settings and in non-educational settings. Measurement invariance is what it is called if we're working from a CFA framework. It is also known as differential item functioning if you are working from an IRT or IFA framework, and they are both concerned with the same kinds of issues. So I'm going to present the most straightforward case of looking at whether or not items measure the traits in the same way across 2 different groups to start with, 3 different occasions as a second example, and then extending those into IRT and IFA models as the next set of 2 examples that I'm not quite done with. But there are more complex versions that I'm hinting at here with respect to many groups, or if you're interested in these same issues but you don't have groups, you have some sort of continuous variable such as age or something like that, there are extensions of these models for that. So just to plant the seed that it's not always about groups, but that is the most common and it is a reasonable place to start. So the big picture then, synonyms: measurement invariance or measurement equivalence or factorial invariance. All of those words are getting at the same idea. So broadly speaking, this concerns the extent to which your items work the same way. Not necessarily that whether there's differences in the trait or not, but it's really, the focus is on how well the items work across different samples, occasions, conditions, etc. The extent to which the psychometric properties are transportable or generalizable. All of those words. Are the indicators working the same way across multiple groups or across time or conditions? If they do, then one's expected response should depend only on their trait. So if an item measures a trait, trait differences should create differences in expected response, and the differences in expected response should have nothing to do with what group you're from. That's the best case scenario. Otherwise, then if the items work differently across different groups, you as the researcher or as the analyst would have to decide how to solve that problem. Whether you are okay with them working differently, or whether you're not okay with it, in which case you might not use that item anymore as a consequence. For those of you who are familiar with differential item functioning, can I see a set of yellow hands for that or thumbs? Diff, as it is called. Diff is a whole thing, especially if you're from the IRT world. I want to warn you that differential item functioning refers to differences in how the items work, whereas measurement equivalence or invariance refers to sameness. Yes, I saw you looking up to the ceiling like, can I reconcile those words? Yes, you can. Measurement invariance is non-diff. Diff is non-invariance. And this is a situation in which the terminology is truly awful. Just let's think about this phrase for a second. Non-invariance. You would think it would just be variance at that point, right? Because you have non and in that are contradicting themselves, but no. It's invariance or non-invariance, or diff or non-diff. And at this point, I usually break down and say, they're either the same or different. Same is invariant. Different is non-invariant, or diff. So even though the terminology is different and backwards, the concerns are the same. What we're interested in knowing is whether the items work differently across groups or time, such that you would have a different expected response that is based on your group and not just your theta. That's not good. Question?
Oh, yeah, I'm just going to ask about measurement invariance.
Mm-hmm.
And then I think I saw it on the
Okay,
text.
did you have, well, ask your question anyway. That way we can all
I
play
just
along.
have a hard time understanding this lack of measurement invariance.
A lack of measurement invariance means the items work differently. That's the more straightforward way to say it. The terminology is horrible. I did not make this up. Trust me, I would not have made up terminology this terrible. But a lack of measurement invariance means that the items work differently depending on what group you're from. The way that the items measure the trait differs.
Sorry, I'm just saying, so the item works differently, depends on what group they're.
Yes. Like an item could be more discriminating in one group than the other, or it could be easier in one group than the other.
Okay, so the group is different trait of people.
A group could be something like whether you are a native Spanish speaker or a native English speaker, and you're looking at the effectiveness of the translation of an instrument. A group could be whether you're a younger adult or an older adult, whether you identify as a man or you identify as a woman. It could also be if you have to take the same test before you start some sort of training program versus after you finish it. Does the test measure the intended trait in the same way amongst novices as it does against trained people? The latter would be an example of a repeated measures group, which you can also do, but the model gets set up differently. So it's not, so the big concern is not whether the trait differs between groups. That can happen and that's fine. It's whether the measurement of the trait differs between groups. Like if I get this item, if I'm more likely to get this item correct because I'm a girl, right, that's not cool. Or if I'm less likely to get this item correct because I'm a girl, then there's potentially something wrong with the item with respect to how it measures the trait. In that case, it could also happen as a consequence of just normal development. So if you think about, say, an indicator of child misbehavior or child behavior problems, something like that. One of the items on such a scale might be, how often does your child bite other children? If your child is 2, that means something very different than if your child is 20. Like grown-ups who bite each other, like that's messed up. But 2-year-olds who bite each other is a day in the life at preschool. So the item means something different in some group than another. And it's a question of whether that makes the item unfair or whether it's just a natural consequence of the item's meaning changing over time or over development in some way. For instance, like before you took this class, if I asked you, how interested were you in learning about how item factor analysis corresponds to item response theory? Like you might say, I'm not interested in that. But after you go through the class, you're like, this is so much fun. I can't believe I didn't know this already. Your answer changes as a consequence of how your understanding of the trait changes. Like, is that good or is that bad? Or is it okay? Because sometimes you understand how to answer a question more after you acquire more content, more understanding of the trait itself or other factors. So Chen Chen, I'm looking at you, because you have a study with 4 occasions, right, of teachers, and you're trying to measure their understanding of epistemic something, or epistemology, some word that I don't know what it means still. What is the word? Epistemic orientation. Yeah, gun to my head, I'm never going to learn what that means. But I know that you can make people understand it more, right, after you help them. And so how they answer questions about their understanding might change as a function of getting more understanding. So how the items work may change as a function of development. Okay, long story short, how the items measure the trait is what we're primarily concerned with. It's only after the point at which we can say they measure the trait in the same way that we can start to talk about trait differences between groups. Otherwise, there's a confound. So the terminology then, to become more specific, we're talking about 2 distinct kinds of invariance. Measurement is one and structural is the other. So measurement invariance concerns the measurement model parameters. In a CFA context, that would be the factor loadings. What else do we have in a CFA measurement model? We'll make this into a review. What else is in a CFA model for a measurement model parameter? I've got factor loadings as one. There's 2 more. Intercepts. One more. Error variances. And just in response to a post I saw on Facebook the other day, who said, you can't call them error variances. I just did, but I would call them not the factor. Whether it's specific variance, unique variance, or error variance, I don't care what you call it, it's not the factor. We have an estimated amount of variance that's due to something else that's not the factor in CFA. If I also covariances potentially too. So if you have 2 items that you think measure something else in common that's not the factor, their residuals can covary for that reason. That would be part of the measurement model. If I'm in item factor analysis land, then what are my measurement model parameters? A and B, that would be the IRT version. Discriminations, difficulties, potentially C parameters or D parameters for asymptotes. What about the factor analysis version of those models? Then what do we have to work with? Not intercepts anymore. Stupid thresholds, yes. And loadings. What about residual variances? Not yet. This is a tricky one. If we're using full information estimation maximum likelihood, there aren't any. In limited information, they're not identified until you have invariance constraints in which they become a parameter, as crazy as that sounds. But that's like 13 slides from now. So the key idea usually is focusing on loadings, either intercepts or thresholds, which is differentiating whether it's a linear model where the factor predicts the item response directly, or a nonlinear model where the factor predicts the link function directly instead. And then residual variances depends on method of estimation. So whether or not we recognize it, we assume invariance all the time. So an hour ago, I was teaching longitudinal analysis, where I'm looking at growth over time in some measured variable. If that measured variable is a scale score, where items are summed together to indicate achievement or depression or some construct that's changing over time, I'm assuming that the way those items relate to that scale score is the same across time. I'm not testing it, but I'm assuming it. Likewise, if I do a t-test on a scale score across groups, you're assuming measurement invariance of how the items relate to the scale score across groups. Even a t-test has an assumption of measurement invariance to it. So does ANOVA for that matter. So this is a bigger deal, I think, than is often recognized, particularly for scale scores or anything where we have item level data that's being summarized into something that we then put in the model directly. So we can't really go any further in making inferences about how groups differ in a trait if we don't have at least some of the measurement model parameters able to be constrained equal and not hurt model fit. Some, but not all, is partial. So if I have 10 items and 8 of the loadings are the same across groups and 2 differ, I'd call that partial measurement invariance. How partial is partial? Technically speaking, you only need 1 to be the same, to link everything together. Only having 1 is a terrible idea, though. Ideally, most. So assuming that you have at least partial invariance, that most of your measurement model parameters work the same way across groups, occasions, or time, then you can look at structural invariance. And that pertains to the structural model parameters, which are the same, by the way, regardless of whether you're talking about CFA, IRT, or IFA. At that level, we have factor means, factor variances, and factor covariances. So structural invariance is whether those terms can be constrained equal across groups. And that is a real question. You might want to know, are people who identify as this group different in their trait amount than people who identify as that group? That might be a real question. And you can answer that real question if you have enough measurement invariance to back it up. So trying to figure out how groups differ. Is it in how the items relate to the trait, or is in the traits themselves? That's the question. Measurement versus structure. Okay, with me so far? Question?
Yeah, like, I'm a little bit confused about repeated measure also. So if I'm constructing like a pre and post test, and I use the same set of items, or I link through same set of some items.
At least some in common, yeah.
So, and I figured out the same people responded differently on the same set of items. So is this considered like invariant?
So the question was, if you have like a pre-test, post-test design where people are answering at least some of the same items in common in both occasions, doesn't have to be all, like if you have a linking design, at least some common set, then say the last part of that again.
Whether we consider this as a measurement invariant or the opposite.
So the question would be if their responses change.
Yeah.
Is it invariance or non-invariance?
It's predicted to be changed.
It's change, yeah, but what is the change? Is it the change in how the measurement model parameters act, or is it a change in the trait? That's what we got to figure out. Because if you just look at the data, you don't know. Because let's say that you're trying to make people learn, so post-test should be higher. If the item means are higher, it could be because they learned and the trait increased and that made all the means go up. Or it could be because the trait's the same, but they remember what the right answer is and now it's easier as a result. So you would have to be able to pull apart those two possibilities. And if like only some items go up but not all of them, then it's more likely a measurement difference than a structure difference. Because you would think that if the trait goes up, all the items go up, like proportionally. So that's what we have to figure out. That's exactly the question, is if there's change, what caused it? Is it change in how the items relate to the trait, or is it change in the amount of the trait itself? The latter, amount of the trait itself, is part of structural invariance. Change in how the items relate to the trait is measurement invariance. And measurement invariance is a logical prerequisite to looking at structural invariance. Okay, other questions? Rumors are good? Zoomers, how are we doing? Are we still alive? 1 thumb, 2, 3, 4, 5, 6. I'm going to keep counting until I see them all. 7, 8. Okay, I got most everybody. I am watching, I promise. All right, so model, oh, now we got a question.
Sorry, I was
No
just
worries.
thinking, may if we have measurement invariance, but we don't have structure invariance, we don't really have control over that, right?
That's right. Then that's not a problem. That's a finding.
Okay. Because only measurement invariance is something we can control.
It may not be something you can control, but it's a problem you'd want to know about so that you could adjust how you're using the items accordingly. So you might make a decision, like if an item is less discriminating in one group than another, to just let it be that way, like just let the loading stay different. And you'd have to make an argument sort of theoretically as to why that's cool. Whereas if you're not okay with it acting differently at all, you might not give that item anymore. So structural invariance is often a hypothesis test that you're interested in, and the answer either way is viable information that you'd want to know about. Do people change? Does this group have more of the trait on average than this other group? Like, those are questions. But we can't answer those questions with any degree of integrity until we know about the measurement part. Okay, question from Nathan.
Yeah, so there's, when we talk about like differential item functioning, do both like differences in like difficulty discrimination, are those both considered measurement variance or?
Yes.
Yeah. Okay.
Yep. Yeah, difficulty and discrimination, A and B, the analogs to that would be A is analog as a factor loading, and B's analog would be thresholds. You can get from one to the other. They're all measurement model parameters because they all describe how the trait as a predictor relates to the item response. That's the common denominator. Any parameter that's per item.
If we're talking about like IRT and like lower like traditional sense, does that cover structural variance at all?
I'm not sure what you mean by Lord.
Like if we're talking about like traditional IRT, you know.
Traditional
3D
IRT.
models.
Yeah, so traditional IRT would use phrases like uniform diff and non-uniform diff, where I'll tell you now, uniform diff is when the B's are different, non-uniform diff is when the A's are different, maybe the B's.
But that's still all under the category of measurement invariance.
Yes, it is, because structural invariance would be the mean invariance of theta, and the covariance is among multiple thetas. Yep.
And we assume that theta is mean of 0, standard deviation of 1, so that doesn't really, you can't really test for structural invariance in that case.
You can, so long as the parameters are linked together so that everything is on the common scale across groups.
Okay, that makes more sense.
Yep. So let me show you how we would do it. How does that sound for a transition? So yes. So if you have independent groups, different sets of people, then we are going to estimate what is known as a multiple group model. And the key here is that each group gets its own factor model, but they're estimated separately but simultaneously. I got a solution for people who identify as this group and a solution for people in the other group, and I get both of them at the same time. That is what's necessary so that I can put constraints and say, hey, make this loading in group 1 the same as this loading in group 2. Make this threshold in group 1 the same as this threshold in group 2. And then at every step we ask, did that make the model fit worse? If it did, they don't want to be the same. If it didn't, same is close enough. So in programs like M+, in the variable section, there will be an option called group equals, and you tell it, what are my groups? In the call to Lavon, it's group equals. So you tell it how you want to divide up your people, what variable in the data set controls that, and you estimate separate models simultaneously, one for each group. If you are doing IRT models using full information maximum likelihood in M+, then the code is a little bit different. You have to trick it into doing a confirmatory mixture model via known class. It's just a coding thing. It's not a mixture model because you know what your groups are. It's just a different way of setting it up. As an aside, there is an approach that's known as mimic models. That stands for multiple indicators, multiple causes, I think. I'm not sure what the second I is, but someone can look that up and tell me. Do you know?
Yeah, that's weird. Yeah, but
Yeah.
it's multiple.
Multiple indicators, multiple
Causes.
something causes.
Yes.
I don't know what I is, but anybody who has Google in front of them, please look up Mimic and tell me what the second I is. That approach is often used to test invariance in a different strategy where you put a variable in your model where it's the grouping variable as a box. And then you have arrows as directed regression slopes of that box predicting your trait and the box predicting each of the item responses. Yes?
What happened with power in these cases? Because, for example, if we have 100 people and we have a variable with two groups, we will be estimating the same structure with these two groups. So we will have one model with 50 people, right?
Yep.
So what about power? Is there any kind of concern
Oh, yeah.
regarding power?
Oh, yeah. Multiple indicator, multiple cause model. The Zoomers told me. The second I doesn't mean there.
Yeah.
So maybe it should be just like mk without the I. But yes, power is always relevant in everything that we do, except that power in this way actually works in your favor. So let's say that you wanted to find measurement invariance, that your items work the same way across groups. A good way to ensure that you will find that is to underpower your study. If I only have 50 people in each group, then I don't have much power to find differences in how the measurement models work. So like, look, it's perfect, it's fine. I have no power to detect misfit. So yeah. Same thing if I had 1,000 people in one group and 100 in the other. Then everything in the 100 group is going to have a lot bigger standard errors. It's going to be harder to detect differences than if it was 500, 500 or something like that.
Do we need balanced data or balanced sample sizes?
No, you don't have to, but you just have to keep in mind that basically the solution, when you constrain parameters to be the same across the two groups, the group that is larger is going to have more of a weight in figuring out what that constrained parameter is going to be. It is the way it is.
Okay.
Yep. Ideally, you would have big groups and big groups of equal sample size. In practice, you get what you get, so don't throw a fit. That's a parenting hack, by the way. Every mother in America has said that at one point. You get what you get, so don't throw a fit, okay? That's when you dare to run out of the green NutriBars and the only one that's left is, red and blue, right? That would be a tragedy at our house. All right, so mimic models anyway. That's where I was going with this. Those models is where you put group in as an observed variable with arrows for direct slopes going to the trait and to the individual item boxes. You cannot test whether the loadings differ if you do it that way. So you can only look at group differences in intercepts or thresholds, not loadings, and that's why that way is not as useful. So we're not doing it that way. So if you have dependent data, so let's say that you have partners of the same relationship, like you have moms and dads, or you have pre-test, post-test, time 1, time 2, time 3, under condition A and then repeated under condition B. Anything that it's the same person answering it multiple ways, that's dependent. Then the way to set up the model is a separate factor for each repeated measure, and they would be correlated. So it would look like this instead. So this is an example from your textbook where we have job satisfaction measured at time 1 and at time 2 by 4 indicators at each occasion. They are in the same model because we have a covariance estimated between what your factor score would be at time 1 and what your factor score would be at time 2. Likewise, this part down here, what are these things?
Error correlation.
Yeah, residual or error correlations. So what they're saying is that because this is item A answered twice, what you said is probably related because it's the same question. So these models start with a default that the same items get to have an extra error correlation over time because it's the same item. It's a reasonable thing. So if you have dependent data, you have to do it this way. If you do it in separate models, as if it's a multiple group data set, that's the same as saying that this covariance is 0 and all of these covariances are 0, and that's probably not true. So this would also be like if you had something like parent report of a child's behavior and teacher report, it would look like this too, because it's the common child that's being asked about in all the cases. So you would have like a parent factor and a teacher factor, and then the answer to question A would have an extra relationship, the answer to question B would have an extra relationship, and so forth. Yeah, that's all I said about that. So another way of thinking about this is that if we had multiple occasions beyond just 2, like 3 or 4 occasions, tests of structural invariance would essentially could become a growth model. Whether the factor changes on average over time, whether the factor variance changes over time, does that sound familiar? Like that's what we did an hour and a half ago. So structural invariance converges into the world of growth modeling when you're working with latent factors as opposed to observed variables. Yeah, I think I said everything I wanted to say about that. Other questions about setting this stuff up? So the examples I have to show you, we're going to start with a 2-group example. Then I have a longitudinal example that has 3 occasions, so it adds a little bit of complexity. But if you can figure it out at that stage, then you can add other occasions or other groups as needed with respect to your individual data. So
Usually the same person is answering the A items.
yes,
We don't expect like a correlation between A1 and B2, for example.
nope. This model says that the only reason that A1 and B2 are related is because the factors are related. That's what it's saying. Now that's a testable hypothesis. And if you are right, if A1 and B2 are extra related, how would you learn about that?
B shows some loadings on the first factor.
Yeah, so
B2.
you would end up with some kind of normalized residual between A and B here that would be positive and big. Like they want to be more together than what the model says. So then you would have choices as to how they could be more together. The obvious choice would be to put another error covariance between A1 and B2. If you had a cross-loading, like you could put another factor loading from this circle at time 1 to this indicator at time 2, that's harder to say. Why does the time 1 factor predicting something that happens in the future? Like that theoretically is problematic. Mathematically, it'd be like, fine. But yeah, this is another type of conditional independence that the reason that any occasions, that any item would be related across occasions is because of their factor relationship. And if it happens to be the same item, they get an extra relationship here too. By the way, if this were estimated as a full information IFA or IRT model, we couldn't have these residual covariances. That's not a thing. Can you think of what we would do instead? What is another way of getting the idea that the residuals are correlated into a model if you can't have residual correlations directly? This is coming in Unit 8, by the way. I'm just foreshadowing. A few of you did this in homework 3.
Is it multidimensional IRT?
Multidimensional, I will take that, but it's a particular flavor of it that I'm looking for. We talked about it at the very end of lecture 5. Another way of getting residual covariances into the model when you can't do it that way. Bifactor, yes, Zoomers, bifactor models. I would make a little factor here and I'd call it my A factor. And I would give loadings from my little A factor to this item A and this item A. And then I'd make a B factor and a C factor and a D factor.
Is that the same as the method factors?
Yes. A bifactor model is the idea that you have extra factors that soak up some other correlation that's not due to the trait, So they're uncorrelated factors. And in this case, because I only have two A's, the loadings would have to be constrained equal. The same thing would be true of my B factor, my C factor, and my D factor. And yes, if this is a CFA model, those are method factors. If this is an IRT model, they're bifactors. And it's the same thing. And I'm not sure if that counts as multidimensional IRT, but it's multiple dimensions, at least. Question? No. Head scratch. Okay. Other questions? So we'll do, this is example 7B, is a situation like this. 7A is going to be your standard multiple group model. We're first doing CFA, and then we'll head into IRT stuff. So here's the process then. So starting in CFA first, and then transitioning into the IFA framework after that. So the first model that we would estimate, I would recommend setting it up as a z-score scaling of your factor. Factor mean 0, variance is 1. Estimate all the loadings, estimate all the intercepts, estimate all the residual variances, and any factor covariances that you need as well. So it would look like this. So then the steps that we would follow, there is an optional first step, that's why I call it 0 as opposed to 1, which is to test whether or not the entire covariance matrix differs across groups. So you would essentially estimate a saturated model for each group and then constrain all the means to be the same across groups, all the variances to be the same, and all the covariances. And you would see if the model fits worse after you make everything forced to be the same across groups. And I have here a comment. Many people, including me, disagree about the necessity or usefulness of this. Can you guess why I don't like this? Why is this dissatisfying to me? To test whether the means are the same, the variances are the same, or the covariances are the same of my items.
I have two
You
ideas.
two? Two ideas, okay.
Yeah, short ideas. First of all, because we are testing against something perfect, maybe that's too much. And the other is that if they are different, we can't know where that difference is.
Yes. So first one, because we're going for perfect, and perfect is not a reasonable goal. Also in the chat, yes, because we're never perfect is not reasonable, especially if we have a large enough sample size where perfect is never going to be attainable. But the second one is really my issue. Like, let's say that we find that this covariance between item 1 and 2 differs across groups. So, like, what am I going to do with that? Is that because the factor differs? Is it because their loadings differ? Like, why? Like, that doesn't help me narrow down the conclusion that I would draw about the mechanism that is responsible for creating those differences. So, to me, this is not helpful. I'll add a third reason. How many potential parameters would I have in a saturated model? A lot, right? So if I'm going to test, let's say that I have, like in my example that's to follow, if I have 6 indicators measuring 2 factors, just the 6 indicators themselves, there's 27 parameters per group. So if I do a model of 54 parameters against a model with 27, like, that's a lot of room for some to be high and some to be low and for the difference to wash out. So testing like 27 things at the same time is not helpful. So we're not going to do this step. But we are going to proceed with the prototypical approach to testing invariance and using this idea as an example. So within the slides, it's a separate idea than what I have for the examples this time. So you can get more instances. So let's say that I have 6 indicators measuring 2 factors. I've got 3 apiece. Each item is measured by only, let me say it the other way. Each item is predicted by only 1 factor. Simple structure is what that's called, by the way. If you only have no correlations among the residuals and no cross-loadings, just each item measures 1 thing, that's called simple structure. So that means the total number of parameters is 27 per group, because we have the number of indicators times indicators plus 1 over 2, plus the number of indicators again for the means. That means that I've got 54 total degrees of freedom. So that's the highest possible number of parameters I could estimate. Step 1 is what's known as configural. And yes, these are standard words that you should learn. Everybody has adopted the same pattern of vocabulary with respect to these things. So configural invariance means, do the groups have the same factor structure? Like, does a two-group model work in both groups? It's like it's at the highest possible level. So the same number of factors, the same pattern of which items measure which factors, and the same conceptual definition. So you can have a little bit of wiggle room. Like you might have one group have one item that has a cross-loading on the second factor and the other one doesn't. Or one group has an error covariance that the other one doesn't. Like you can have little differences, but broadly speaking, both groups should measure a factor using the same items in roughly the same way. So the way that we would do that is to estimate a model in which the same factor model is estimated for each group, but everything is estimated separately. So it's like each group gets their own version of everything, it's just happening simultaneously so that we get a combined test of fit. And that then is the jumping off point, because everything we do subsequently is going to make the model worse, because we're taking away parameters, we are simplifying, we are applying constraints. And the question will be, is it significantly worse or non-significantly worse? Yes?
In these steps, we are not comparing between models. We are comparing each model with, for example, the H1
Yes.
in each group, looking at the RMC, CFA, TLA. That's the reason.
Yes. So the idea is that the same type of model should fit well in each group. Otherwise, there's no point in going forward. Because if you're not measuring the same things, then all of the subsequent tests about how the items relate don't make any sense. Now you can have, like, there are ways to force it into being the same. So let's say, for example, Chen Chen, I'm going to call on you again. You're supposed to have 4 factors, right? At time 0, do you have 4 factors? Do you know yet in your dissertation? You think you do? Okay, so let's say hypothetically that you analyze your equations separately just as a starting point, and you run your 4-factor model at time 0, your 4-factor model at time 1, your 4-factor model at time 2, and so forth. And let's say that at time 0, it's only 3 factors, like they converge into 3 instead of 4. You could still have configural invariance if you keep it as a 4-factor model, but then let the correlation be 1 between the ones that want to go together. Then it's 4 factors, like from the perspective of estimation, but conceptually it's only 3. That would still allow you to proceed with all of the other tests, because then you're still working with a 4-factor model.
How about the 4 factors? You have more than 4 factors when I analyze each factor is 7 factors.
What about, can you say that a little louder, please?
Yeah. So in homework 3, I analyzed the 1 factor, and finally I find out it should be 2.
So in homework 3, she thought she had 1 factor. It turned out to be 2.
Yeah.
You and like everybody else, by the way.
And then we hypothesis the extended orientation has 4 factors, but maybe at the end it has 6 factors and 7 factors. So how should I?
So if you have a different number of factors, like basically if you find that in one group it's 2 factors where the correlation is less than 1, let's say, and in a different group the correlation is not different than 1, so it's only one thing, you can still set it up as if it were 2 and just allow the correlation to be perfect. Because you're going to let the factor covariances be whatever they want to, and that will make it estimable. Each group is going to get its own pattern of factor covariance until the very, very end of this process. So it's still okay. Yeah. It would be a different thing, like in terms of, oh goodness, I'm trying to think of an example. So there are types of hypotheses that would be addressed at this stage with just this question. One of them is in the concept of human development, there's ideas of differentiation and de-differentiation. Have you heard these words before? So as an example, if you try to measure executive function in children, so executive function is like inhibition of control, planfulness, like all the things basically that your brain needs to be able to do to get around in this world. And the measures that they give to like 3 or 4-year-olds, executive functioning is one factor. Like it's unidimensional. But as kids get older, it spreads apart. Like you can have strong inhibition, but do badly on planning, like it splits apart. And then the reverse happens in older adults. Things that look like they were separate dimensions start to converge into one. And so whether or not like you have one factor over time that turns into 4 factors back to 1, like that's a question that people might have. But what you can do is even if it looks like one factor, you can still specify all 4, but just allow the covariances to be perfect so that conceptually it looks like 4, but it's really 1 still. That would allow you to continue with the invariance testing. Okay. Other questions or examples? Yes?
So for one of the survey scale I'm considering to using is measuring language and anxiety.
Mm-hmm.
Then within language there will be 4 different skills, like listening, reading, writing, and speaking.
Mm-hmm.
So when you have, for example, 4 items to measure each part, are you end up having one factor like an overall anxiety, or it's more like you will have 4 small factors like writing and anxiety, listening and anxiety, speaking and anxiety, reading and anxiety, like that?
Mm-hmm.
Can I still do I have to specify, or can I still use the 6th item to measure language?
So the question was, if I have an example of, when someone's learning a foreign language, they have to do writing, speaking, reading, and what was it, the 4th one?
Listening.
Listening,
Yeah,
okay.
well,
Writing, speaking, listening, and reading.
Mm-hmm.
And so you can imagine that in people who are just learning a language, they can't do any of it,
Mm-hmm.
and it looks like one factor.
Mm-hmm.
But then as you grow in your capacity, for me, it's a lot easier to read Spanish than it is to say it.
Mm-hmm.
And so my skills start to become uneven in my development, and other people's might become uneven in different ways. So it splits apart. So if you have 4 factors, in groups that don't have all 4 yet, what I'm saying is that you could force them to have all 4, but or just let the covariances between them be 1. So they're 4 perfectly correlated factors is the same thing as 1. But specifying it as the 4 allows you to go forward in this process to compare against a group in which you really do have 4. That's what I'm trying to make. I need a picture for this. I'll make a picture and add it to the slide deck. How's that sound? There's too much doing the gestures here at this point, so. Okay. So yes, the big picture here, everything we do from this point forward, it's worse or not worse, because we are taking parameters away systematically. That also means that if you don't have good model fit, you're done. Because everything you do is going to make it worse, and the worse the model fit is, the less you can trust the inferences you're trying to make. So in CFA, all of the invariance testing that we're going to do is via likelihood ratio tests. So within maximum likelihood estimation, it's just the straight difference in log likelihood multiplied by -2. If you're doing robust maximum likelihood, then you have the scaling factor correction that shows up in the calculation. So here is another link to where it's explained on the MPLUS website. I still have a spreadsheet for this, and they're posted along with this example. And in Lavaan, for these models for CFA, the ANOVA function does get it right most of the time, but not all the time, I've learned. And I don't know why that is yet. I just know that I was not able to replicate everything I had done in MPLUS. So in general, when we're doing model comparisons, if we are removing parameters, then the test statistic tells us whether that removal, that simplification, made the model fit worse. That's a significant result. If the test statistic is non-significant, then we would say it's not worse. Not worse means close enough, it's fine, you can make them the same. That's very different than what we're doing most of the time in building a factor model, which is adding things. So if you start with what you thought is a one-factor model and it looks like it should be two, you are adding a factor covariance. And so then your test statistic is going to tell you whether that addition makes it significantly better or not better. So I'm hammering this home because I've seen people in results sections in writing talk about this backwards. If you're taking things away, you cannot make the model better, not in terms of absolute fit. It can only be worse or not worse. Now, some of the fit indices like RMSEA, do you remember what's special about that one? RMSEA is relative to perfect, but it is how off you are divided by model degrees of freedom. So RMSEA gets selectively happier with you if your model gets simpler. So it is possible that your model, you could take things away and RMSEA says it fits better because it's a simpler model. But in terms of log likelihood, that cannot happen. It's worse or not worse. Here is the likelihood ratio test for LMR. The rescaling formula, again, this is the extra piece where you have to multiply the difference between them by this thing right here. So just to remind you that that is an extra step. If you're in standard maximum likelihood, the scale factor is 1. So you can still use the same spreadsheets, you just enter 1 in both places. Okay, so in an example here, let's say that we have 6 indicators, 3 indicators for each of 2 factors. So in the slides that follow, I've got the model parameters for group 1 and for group 2. 1 is going to be denoted as what we call the reference group, and 2 is going to be the alternative group. So this is the same language that we refer to when talking about like the effect of a dummy-coded predictor. Like for the group 0, that's the reference, and then the parameter talks about how the other group differs from that one as the alternative. So it's up to you who's the reference and who's the alternative. It really doesn't matter, but you just have to set it up in the code as one or the other. So group 1 is the reference, group 2 is the alternative. So if I have 6 indicators per group, then each group has 27 degrees of freedom to start with. That's the number of means, variances, and covariances across my 6 indicators. 27 parameters per group times 2 groups gives me 54. Now, how many do I have to spend to estimate this model? Well, in group 1, I have 6 intercepts. I have 6 factor loadings, and I have 6 error variances. That's 18. I have 6 factor loadings, 6 intercepts, 6 factor loadings, and 6 error variances in group 2. That's 36. Now, how do I identify the model? Remember what my choices are for identification? How do I identify factor variances? What are my choices? Something's got to be 1, right? What are the 2 choices to make 1?
One of the indicators in the factor? Or
What about
same
the
as
indicator?
One? Should be the factor loading should
The
be
loading.
1.
Yeah, so I can fix one of the indicator factor loadings to 1, or I can fix what to 1?
The factor variance directly.
Always read from the slide. Whenever I ask a question, the answer is usually up there. So yes, in this case, I'm fixing the factor variances to 1. So they don't count as estimated parameters. Likewise, what are my choices for scaling the factor mean? Something got to be 0. What are my 2 choices?
The
The factor mean is
itself,
1, or I could do what?
Fix the item intercept to 0.
Yeah, one of the intercepts could be 0. Now, I am choosing this deliberately for reasons that will be unveiled shortly. Yes?
I thought that in the market item option, we didn't have to fix the item intercept to 0 because, because that item intercept is passed to the factor mean, or that's incorrect.
That is one of the 4 choices. So there's a 2 by 2 of what gets fixed and freed. And the most common option is one of the items has its loading fixed to 1 so that the factor variance can be estimated. But that same item would still have its intercept estimated so that the factor mean must be 0. That, it's like an off combination. That's most frequent.
Okay.
It's very rare that you would free the factor mean and estimate, or free the factor mean and fix one of the intercepts to 0, but that is a choice.
Okay.
That would show up in longitudinal analysis more frequently. But in this case, I have identified each group separately, okay? Key idea here. These groups are being estimated, their factor models are being estimated simultaneously, but they are not on the same scale yet. Because each group has a factor mean 0 and a factor variance 1. So I'm counted up to 36 parameters. What are the other 2 that I'm missing? What haven't I counted yet? Factor covariance, 1 in each group. That's the other 2. So here's my list of all the things. So that's why I end up with 16 degrees of freedom. Okay, so this is my jumping off point. This is the best we're going to do in terms of fit. Next model. First question concerns whether the factor loadings are the same across groups. This is known as 2 different sets of words. One is metric invariance. The other is weak. So it's weak, strong, and strict are 3 levels, and so this is like the easiest one to pass. That's why it's called weak. Metric is what I prefer to call it because that's more descriptive. But in a paper, I would say, I tested metric invariance and then immediately in parentheses, equality of the factor loadings. Like, always say what it is, as opposed to just relying on people to have memorized the vocabulary. But the first question then is whether or not the loadings are the same across groups. So whether the extent to which the item discriminates across people is the same across groups. So this is not a tau equivalent model. It's not that I'm saying all items are equally discriminating. I'm saying that item 1 is as discriminating in group 1 as it is in group 2. So item 1 is as good at measuring the factor in group 1 as it is in group 2. So a critical step then is to simultaneously allow the factor variances to become estimated in the non-reference groups. Because one of the reasons why the factor loadings may have been different across groups is because the factors had different variability. So if we think about this with our regression hats on, what is a loading in just linear model terms? Give me a synonym for loading that starts with an S. Slope. Definition of a slope, change in y for a 1 unit change in x, right? So if I take that idea and put it into our story, what's y? Item response, what's x? Factor, theta, trait, whatever you want to call it. So one of the reasons why a slope, which is in a metric of y per unit x, may differ is because what a unit of x is differs. So if groups have different factor variances, that could propagate to different loadings because this model says they're both 1. So we have to release the factor variance to let it become an estimated parameter in the alternative groups. It stays 1 in the reference group for identification. And now, with respect to the factor variance, both groups are on the same scale. So it would look like this. The difference relative to the configural model is in bold here. So rather than having a separate loading for each item across groups, I have made them the same. The way that we will do this in the software is to give them the same label. So like I would say, this is L1 here and L1 here. This is L2, this is L2. This is L3, this is L3. So note within a group, it's still 1 through 6 because we're not saying the items are equally discriminating of a factor. We're saying they're equally discriminating across groups. So I have saved what would have been 6 parameters, but by forcing the loadings to be the same, I have to free the factor variances in the alternative group. So that's where the 2 come back. So the total degree of freedom difference relative to the previous model is only 4. Previous model had 16 degrees of freedom. This one has 20 because I freed up 2 factor variances, but I constrained 6 loadings. So the net change is 4. Yeah.
So we are constraining 2 of the factor loadings in the second model.
We are constraining only factor loadings to be equal to each other.
Okay.
But in doing that, we have to free the factor variances so that we're not inadvertently making a structural constraint too. So another way of saying this is that if we let the factor variance differ, then we've eliminated all the reasons why the loadings would have differed. And if they still differ, then it's for something else that's not the factor. So it's a proportionality constraint, essentially.
So is this the same that if we would constrain that factor loading to 1?
Yeah, that was actually going to be where I was going to go next.
Okay.
So what would happen if instead of identifying my model so that I had factor variance fixed to 1, if I had used a marker item? So let's say that I used item 1 as my marker for factor 1, and I used item 4 as my marker for factor 2. Could I have done that?
Yeah.
Sure. Now, could I test then whether 1 is different than 1?
No.
No.
Okay. Okay.
So that's why you don't do it this way. That is still the most common way I see people do it, but it's incorrect because you are assuming that 1 is equal to 1, and you don't know that. There is no other alternative when you force the loading to be 1 in both groups. So if you set it up this way, if you fix the factor variances to be 1 in the reference group, then you can test all the loadings and not assume any of them are invariant.
So could we test that if we have like the first item, the distribution of the responses of the first item for the 2 groups are very similar, so we can assume that this item could work as a marker item?
Only looking at the distributions would not tell you which part of the distribution was due to the factor versus not the factor. And we're concerned with the factor part specifically. So I get a lot of questions about this, but I will defend this, I will die on this hill. Do you know that expression? It's an expression that means like this is a big deal and I will fight about it as opposed to just like letting it go. I will die on this hill. No. This way you can test all the loadings. If you do a marker item, you cannot test that loading. And what do you think happens if you falsely say that they're the same and they're not? Everything else is going to be wrong because you're linking 2 things together that shouldn't be the same. So at this stage, we would constrain the loadings, free the factor variances, and then test the difference in fit where the only possibilities are worse or not worse. So this would be 4 degree of freedom test. Yes?
There is something confusing to me, but if now we are estimating in the second group the factor variances, what is fixed?
What is fixed?
Yes.
The factor variance is fixed to 1 in the first group. So they are sharing a scale across groups now. So what a 1 unit change is in the same metric now across groups.
Okay.
It's the same scale in the first or in the second?
The factor variance is on the same scale across groups through the shared loadings.
So the second.
They're shared together, but where they're nailed down to is the first group has the 1.
So the first group might have different scale?
The first group's factor variance is setting what 1 means. Like it's setting the key of the model, it's setting the scale. So if the second group is more variable, its factor variance will be estimated as some number bigger than 1. If the second group is less variable, its factor variance will be estimated as some number less than 1. So before, in the configural model, they were not on the same scale at all. It was like 2 different definitions of what 0 and 1 meant. because it was group specific. Now, through the constraints on the loadings, we have linked them onto the same scale. So the variability of the factor means the same thing across groups at this point. The variability of the means, though, is not on the same scale yet. So this model is like partially linked, but not all the way. Question?
Back to the unbalanced weights of the two groups.
Mhm.
So could we fix the variance of the, for the first group put in one and for the other group another number, resolve the issue of not equal weights or not equal people in the two groups?
I don't know that that would help any.
I'm thinking that one standard deviation would include more people for the group that contains more people than one standard deviation in the
I
other
see.
group.
So yeah, I think that the estimate of the factor variance is going to be more precise to the extent that you have more people. So from that perspective, might be wise to have the alternative group be the larger of the two. But the way that I usually see it in practice is the opposite. The reference is usually the larger group. I don't know that anyone has looked at that. That might actually be a research question that one could investigate, is whether that matters or not. My instinct would be that it shouldn't, but I don't know that for a fact. Because I agree with your logic. Like, if you really care about the estimate of the factor variance, then having more people to go into that should be a better strategy.
Yeah.
That logic to that part sounds familiar. Sounds reasonable. Yep. So if this fits not worse, then what we would conclude is that the items measure the trait in basically the relationship between the response and the trait is the same. So to most people, this is the most important step, and that's probably why it's first. Because most people would use the loadings as part of their basis for what the factor means, how you would interpret the factor, let's say it that way. So like if you have 3 items that have very strong loadings and 3 items that have lower loadings, like you'd say the factor is more of this, whatever that is. And so if you're able to say that like the same pattern holds across groups, then the factor definition is more the same. Whereas if you don't have equal loadings, then it's harder to say you're actually measuring the same latent trait. You can say that you have a factor in each group, but it's not the same factor. The loadings help define what it means in relation to the content. Does that make sense? Yeah. So in most cases, though, you're going to get an omnibus test. So you're going to constrain all the loadings. You'll get a result that indicates model fit is worse. You got to figure out why. And this is where we are actually going to use what I previously called cheat codes, modification indices, but they're not cheating this time. They will tell us which loading is the one that's causing the increase in model misfit, or which loadings. And that can tell us which one might need to be free. And if we free that one, then maybe the rest are okay. So that's where the process can get quite tedious. Is, okay, this one, all right, free it, check. Still worse? Okay, crap. How about that one? Free it, check. Still worse, crap. Okay, free that one. So it's very iterative. And if you're thinking, wait, isn't that capitalizing on like sample specific and type 1 error? Yes, you're absolutely right. So this process of when it looks like it doesn't work, what do you do next? There's like a million different permutations as to what people would do. I'm showing you sort of the classic SEM literature, what people would do, but there are other options that people have put forth, and even automated routines that would like go through and try things one at a time in all permutations. So there are packages that will do the permutations, for instance, and some of the IRT software. So the process of figuring out what needs to be let go and what needs to be constrained it's subject to a lot of error. But that's the way it works. So our goal then is to get most of the loadings. And if we can get most of the loadings to be the same, we say we have partial invariance and we can go forward. So it's 3:12, which means I should stop now. But I will warn you, your very first example is taken from the Brown textbook directly. And everything works perfectly, as it does in almost every textbook or tutorial paper I've ever seen on this. Everything's invariant. Everything is great. I'll show you that one, and then I will show you a series of examples where it all falls apart, because that is what actually happens in reality. So the descriptions of this are very like rosy and optimistic for my taste. Question?
Then, so for the scalar invariance, we will have the same thing, fixing the factor mean at 0, and then the scale will be shared.
The next step, we constrain the intercepts,
Yes.
release the factor mean, and then the scale is fully shared across the
Great.
two sides. Yep, that's
Okay,
where I'm
that
going
makes sense.
next.
Okay.
But you're going to have to wait till Thursday,
Yes.
because we're out of time. All right, any other questions before we call it a Tuesday? All right, then I will say thanks for being here. Office hours tomorrow if anybody needs help with homework or whatnot. Otherwise, I hope to see everybody Thursday. Have good afternoons.
Thank you.